All right, welcome back. We are Game 3001. That's Artificial Intelligence for Games in the summer 2022 semester at George Brown. And it's week 11, part 2 of our broadcast and recording. Again, this semester lecture happens after lab. We had our lab on the Tuesday. All right, so welcome back, guys. So this week we're talking about behavior trees. Last week we talked about state machines. We also, in Lab 6, created a bunch of path nodes. Each path node had line of sight capabilities. We did that last week. And this week what we did was we took the stuff from, I gave you guys a brand new starter. And what we did this week was we built a very simple decision tree to help you with assignment 3 and 4 and 5. Okay, that's what we did this week. Again, just a reminder that assignment 3 is due this Sunday at midnight. And if you haven't signed up for groups of up to 3 members already, please do so at your earliest convenience as, again, this one's worth 10% of your final grade. We're sitting here at week 11. So the week of July 18th. Today is July 21st. And today it's all around behavior trees and how they differ from state machines and decision trees. So far we've covered 2 types of decision-making algorithms, and now we're going to go into a third type. And these are the 3, I would say, most popular types out there in the industry so far. So let's get into what they are and what's happening. And we'll come back to an administrative kind of call for stuff that's missing, because I got to talk about that a little bit as well. So, so what are behavior trees? They have a lot in common with hierarchical state machines in some ways. And we'll talk about hierarchical state machines. Remember, there was an alarm condition, and that alarm condition was the thing that kicked us out of normal operation and then, kind of swung us into another state altogether. And a good example of that is last week we talked about if a player or an autonomous character has taken damage, that is an alarm condition. They have to do something, again, according to our assignment 3 and 4, right? So let's suppose that is an alarm condition. And the alarm condition, what it does is it stops regular decision, whatever the current state is, and then they move, you move the autonomous character into a new state based on the new condition. But instead of state, the main building block of behavior trees are tasks. Okay, that's what they are. And tasks are composed into subtrees for more complex actions. They can be very complex. And actually, behavior trees are the preferred way of building out, I would say, decisions. And I'll say that, I'm going to say it up just to say it as a general statement. And the reason why I'm saying it is because the amount of complexity you can add when you're using behavior trees is pretty intense. And we'll show you what I'm talking about here in a second. So trees that we'll look at today have these 3 types of tasks. And actually, we've looked at 2 types of tasks like this before, conditions and actions, right? And then the other type of task we haven't seen so far, we haven't talked about anything like this, is something called composites. Okay, and that's either a selector or a sequence task. Okay, so conditions, something that tests the property of the game. Actions, something that alters the state of the game. That's what they look at right now. Okay, so that's what behavior trees are going to be broken down into. So let's talk about composite tasks. Starting off, composite tasks, they run each of their child behaviors in turn. Okay, so that's one thing that happens. So you have the composite task itself might be the root of the behavior tree. Okay, and you have 2 main types of composite tasks. One of them is a selector type task, and the other one is a sequence type task. Okay, so a selector, it really what you're trying to do is it either returns with a success when only any one of its children returns successfully. Okay, so think about this as an example. There might be 2 things or 4 things that can happen with a selector. I want to select the task that is successful. The first time I return with a successful action, I stop the selector task altogether. Sequences are basically, we want to run the entire sequence And if any task fails, the entire sequence fails. Okay, so we're going to talk about how this works a little bit. So here's an example of a selector. So again, any one of these children can return true, and then this whole selector tree returns true. Notice that we were talking about, for decision trees, we prefer binary decision trees because they're like either left or right, true or false. Very, very simple, very quick to make a decision. Here, you know, as an example, we might have several different, you know, kind of tasks, subtasks that we want to perform, and they're linked to the main selector. So again, the selector is the default icon is some kind of question mark like this. And then what you have is any one of these tasks. So for example, if I can attack, if it's true, then I return true, and then I'm done with this, with that behavior. Simple as that, right? If I want to taunt them or stare at them, any one of these that are successful, if let's say if I can't attack because I'm too far away, then I can taunt them. You know, if that's successful, if they maybe there's a condition that says I was successful by taunting them or staring at them, you know, as an example, that might return true. A sequence task, though, or a sequence itself, a sequence node, kind of does something like this. Okay, is the enemy visible? True? Good. Come back to here. And we can say that the sequence is running. So this current sequence is in running form, right? So I go back to the sequence, you know, kind of node itself, the main node. And then what I do is, okay, now try the next task in order, right? So I'm running these things in order from left to right. So, okay, turn away. Can I turn away? Yes, cool, run away, all right? So that is kind of the order. But let's suppose the enemy's not visible. So this is kind of an X, right? And I'm going to just annotate this. Let's say I can't do this. As an example, that the entire task fails, right? Whereas in the sequence or the selector, if I can do any one of these, let's say, for example, I failed this one, well, I'm going to try this one. If this one passes, then this one, this whole thing passes. But if any one of these fail, the entire tree fails. That's how the difference between a selector, for the most part, and a sequence. Okay, so that is a composite set of tasks. So why am I saying these are building blocks for creating your behaviors? Okay, that's what they work out to be. One thing to note is you can combine selectors and sequences to come up with a very complex behavior kind of tree altogether. So again, the simplest behavior tree would be something like this: move into the room. That you're just going to do that. And the more complex one would be something that looks like this, where, okay, so here's a selector. So let's look at this together. And I'm just going to zoom in here so you can understand. So again, a selector, question mark, either one or the other, any one of these. The first one that runs true, then I return success at the top. Any one of these can return success. Let's try this out again. And I'll use, you know, the check mark. Okay, so I start with the leftmost task. The leftmost task happens to be, in this case, a subsequence. So a sequence task. Okay, now I keep going to the leftmost task. Is the door open? Okay, if the door open is no, right, it returns false. If any one of these two tasks returns false, then the whole node returns false. This is a sequence node. So this node returns false. Okay, because it returns false, I return false here, and I try the second sequence. Okay, so if the door is not open, I'm not going to try and move into the room. In other words, this whole tree, this whole subtree is now false, as an example, right? So now I try this sequence. Okay, so I move to the door, check mark. I can move to the door. I open the door, as an example. All right, check mark. And then I move into the room, check marks. Because these three returned all true, then this whole sequence returns true, which this kind of subtree returns true, right? Therefore, this returns success. So it's very interesting. I could have two conditions really. Either the door is open or the door is not open. So this would be like the door open side. This would be the door not open. And you can see that there's a couple of nodes here that are repeated. All right. So for example, the move into room is the exact same thing. Those two are the same, right? But so these would be the actions you're going to take. Okay, these are the actions. But these ones here, this action is different, this action is different, this action is different. Okay. So you can also relate it to something like this. If the door is locked, right? Then move to the door, open the door, move into the room. All right. So this is kind of a way of doing it as well. So if you think about it like this, okay, almost like an if statement. Okay. So clear so far on the differences between selectors, that's these ones, and sequences. Sequences are these ones. Okay. So selectors and sequences. Again, it's very interesting the way this can all combine to make it very, kind of straightforward. There's other types of nodes as well. We're going to talk about them. So those are the kind of a couple of nodes. They're called composite nodes. Here's a more complicated refactor tree. Okay, a more complicated one. So let's take a look at this. Okay, now in this case, the top one is a sequence, except that there is only one node in it. That means this node must return true in order for the sequence itself to return true. Okay, as an example. Okay, let's take a look. So here's a selector. Either this one or this one can return true. The first one that returns true is going to return true for the entire subtree, this part right here. Let's take a look. So the door is not open, so this returns false. Let's try the second branch. Okay, now we're into a sequence. The sequence must, both of these two must return true for this branch here to return true. So can I move to the door? Yes, cool. Can I open the door? Yes, cool. Therefore, this whole thing is true. And because this is true, this returns true, which means this sequence itself is true. So again, very different ways of refactoring things, to kind of have the same type of behavior. All right, so again, back to you guys. Get it? Are you good with what I'm trying to say? This is just another way, a different type of tree structure. Again, it's a different data structure. So you have a tree, but in this case, instead of having a left node and a right node, I'm going to have, depending on the type of root node that I have, whether it's a sequence node or a selector node, I might have, as an example, the response that's going to happen. What I'm waiting for either is every node in my sequence has to be true in order for the whole sequence to pass. If I'm in progress, that means that in a sequence, that means that I haven't completed the entire sequence. I'm in somewhere in the middle. I haven't gone through each of the children in my sequence. I haven't done that. Okay, and until I reach the last child in my sequence, and all of them return true, I'm still in progress. I'm still running. That's my status, if you will. So a sequence would have a status. I'm running or I'm not. And so would a selector. A selector is running or it's not. Okay. And a selector, any one of them, the first node, the first child that returns true, the entire selector is true. Yeah, that's how it works. Okay. So that's how this works. Let's continue. So here's a behavior tree for an enemy. All right. So again, you have a selector node. Again, we're taking a look at these so that way you can get used to them, right? That's why we're kind of talking about this for a second. And let's zoom in again. So here's a sequence, selector. Selector, again, any one of these two subtrees could be true, and the whole decision is true. All right, let's take a look. So now I have the left child. The left child basically is a sequence. Is the door open? Again, let's mark it as no. Right, so we'll make it so it's red. So let's say if the door is not open, so no, then okay, then this whole sequence fails. So I can't move into the room if the door is not open, which makes sense. Right? I can't do that. So we can say that this node failed. All right, and because this node failed, we're back here at the selector. Let's try the second, the right subtree. Okay, now for the right subtree to work, it's a sequence again. All members of the sequence must be true, okay, in order for it to work. Okay, so can I move to the door? All right, so yes, I can move to the door, so check mark. All right, I'm back to here. I'm in progress. Okay, so now the second child is actually another selector. Okay, so selectors, again, either one or the other, any one of these could be true. So we're going to go down in here, and the left child of this selector node will have the first, again, for the selector or the sequence to work, both door locked and door open, right, have to be true in order for this side to be true. So is the door locked? The answer is yes, it's true. It's locked. So let's mark it as true. Cool. Back to here. Can I open the door, right? And if I can't open the door because I don't have a key, right, then this node would fail. So let's say, for example, this node fails. And because this node failed, and this sequence needs both nodes to succeed, this sequence node fails. So I try the second side, the next branch. Okay, cool. So let's try this out. So now, can I barge the door in? Yes, I break the door down, let's suppose. Okay, great. And is the door open now? Yes, the door is open, and therefore this node succeeds therefore this node succeeds. We go back to this sequence, and now finally I can move into the room, and so this node succeeds, and therefore the entire sequence succeeds. Here's an example of how that decision would work. So you can see that there's more complexity here. We have a lot of options here for how to make this work properly. And I think this is, it creates a more complex behavior, right, scenario, especially when it comes to something like this, right? Could you code a state machine to work like this as well? Sure. Could you code a decision tree to work like this as well? Absolutely. But it might be less intuitive than something that looks like this, right, when you look at it. So that's why we have a different kind of structure that serves us in a different way. Again, what would really be nice is if we had a visual scripting language that allows us to kind of draw nodes and connect them and then create a behavior from the nodes. And again, Alex and I are working on that right now for our little engine that we made, but other commercial game engines have that. For example, Unreal Engine has a behavior tree construct, kind of something that you can create behavior trees with visually, as opposed to something that you're going to make, kind of manually. All right, so when we think about behavior trees and I want to implement them, they're made up of independent tasks, right? Each with its own algorithm and implementation. So the task itself is unique a lot of times. All of them conform with a basic interface that allows them to call one another without knowing the implementation details inside. It's a black box, okay? And let's take a look at the implementation details. So here's an example of a task superclass, okay? And remember, we've been talking about everything as a task, right? So really what we want to do is return either true or false. Did the task, succeed, or did the task fail? Okay, and so all tasks are going to have a run function that's going to be unique, that unique task, right? The unique to the task. And that run function is going to return a Boolean, either true or false. It ran or it didn't run, okay? And there'll be criteria inside of the task, as an example, that either will prevent it from returning true or ensure that it returns true. Okay. Here, as an example, class enemy near extends a task. Right. So as the enemy near is again one of the tasks. So it's a type of task. And here, as an example, it overrides or because remember we have a run task that would be, this is the interface, right? The abstract superclass. Let me just mark this as what it would be. And again, I'm talking about coding because I want you to think about how you would code this based on our lab this week. So this would be an abstract superclass. That's a weird color. Let's see if I can change the color to something else, like, I don't know, blue. There we go. So that's an abstract superclass, right? And this would be a child class, right? So this would be a concrete class. Concrete class is what it does is it's something that you can actually instantiate. An abstract class, remember from your learnings, is something you cannot instantiate, that is used as a template for other classes. So here in the concrete class, we want to override the run task, the run method or function. We want to override it. And it says the task fails if there is no enemy nearby. So here's the example. It's going to return the distance to the enemy if it's less than 10 or not, if it's less than 10 pixels. If this fails, then the whole task fails. So enemy near would return false if the enemy is not within 10 pixels, let's say. Okay, that's how it would work. Okay, so abstract superclass, concrete class. Here's an example of a task. okay, that you would check for. All right, so that's that part. And let's move on. So here's an example of if I want to play an animation. So I'm going to play the animation as an example. And the only way I can have this animation return true, because it's going to do the run method, the run function in these class play animation, is if the animation engine is ready. If the animation engine is not ready, it's going to return false because it's just not ready to play. Now that would be almost impossible. So chances are, I mean, it's impossible if your animation somehow engine is not ready. The only way that's not ready is if something went wrong, right? But so this is kind of a weird example, but you know, again, what you want the animation engine is to play whatever the animation is at whatever speed you want, and then return true, saying, "Yep, my animation is playing." Okay. So again, this play animation extends a task. But so too do selectors and sequences. Okay, so a selector is a type of task, okay, but a selector has a bunch of child tasks that are linked to it. Okay, so these are the child tasks here. It's really what it is a task array or a task vector. Okay, so remember what selectors look like, right? If we go back here, that's a selector, and it has one or more children. So child tasks that are going to run. Okay. And here's the run. It's going to return a true or false, and it says for every child in children, if I'm able to run any of the children at all, if I can run that task and if it's true, the first child that runs true, then I'm going to return true, return out of this for loop. Otherwise, I'm going to return false. So this is an example of how a selector, any one of the children returning true, is going to make this selector return true. At the same time, sequences run a little differently. They have, again, an array of tasks, but in this case, for every child in the children array, if any of them run false, right, then the entire task returns false. Otherwise, it returns true. Okay, that's how it works. So again, and again, you can check for status. You can communicate status up to the previous task, to say where this is in the sequence or in the selector by basically having a state or a status, and you can have a custom status that's saying something like running, or failed, as an example. So you can actually have a status up here, and you can create an enumeration to keep track of whether that task passed or failed, if you really want to. So from a performance perspective, it's not bad. It's not quite as good as when it comes to a decision tree, but in terms of the way it works, it's a little bit slower than a decision tree because of some of the complexities, the way things are linked together. Again, still, pretty fast. All right. So before we kind of go away from selectors and sequences, it's worth looking at some variations. Okay, so again, the implementations that we just talked about, they run their children in a strict order, right? And the order is defined in advance by the person defining the tree, just like how we were defining the tree manually in lab 7.1. And we kind of said, hey, you know what? I want to define the tree. I'm actually building the tree by hand. That's what we did. And when we built the tree by hand, what we kind of said was, this is a very specific tree for a close combat enemy. That's what we kind of said in lab 7.1. Similarly, when we're building a behavior tree, it's deterministic. It's going to follow the exact sequence that we tell it to follow. However, sometimes what we can do is we can, try, different, kind of parts of the selector first. So the reason why this would be good if we swapped things around sometimes is it would give some randomization or variability in what the behavior of the AI is going to be. So sometimes it doesn't make sense though. So if I looked up here, and if I took a look at some of these, this diagram, if I chose, this one instead of this one, so I choose one of the children randomly in the selector, let's suppose, right? Unless I choose this one, right? Well, if I choose this one, it says move to the door, right? I'm sure I moved to the door. That's the first thing. So let's say I did this one first, right? And then I'm here at a new selector. and then I can do these two, and I run a random one. So I do this one again. So I barge through the door. Is the door open? Yes. I don't even try to see if it's locked or whatever, or try to open it. I just barge through, right? And then, yes, it's open. I go here, and then I move into the room. So this could be randomized if you think about it, right? Because I don't have to follow this strict sequence, right, in this case. However, individually, sometimes it doesn't make sense. If I go here to the sequence, right, and I say, okay, I want to move into the room. Well, I can't move into the room because the door's closed. Well, this fails, right? So it's kind of, it may not make sense, is what I'm saying. Same thing here. If I go into a sequence and I say, I want to do this one first, well, move into the room. Okay, this whole thing fails. So I don't even try and barge the door or, check if the door is locked or any of that stuff, right? So, you have to make it so that you have to, when you're constructing your behavior tree, if you want to make it more or less deterministic, you have to kind of plan ahead of time. So, what we want to do is we want to avoid predictable AIs. And I talked about this last week, and I talked about it the week before, because predictable AIs are, well, predictable, and that way you can defeat them. Okay, you know what they're going to do. Or you have a good feeling. You've seen their behavior a bunch of times, so you know what they're probably going to do. Some of them are going to be a little bit more aggressive. Other ones are going to be less aggressive. If they get hit, they're going to, kind of go behind cover. Like example, the predictable AI we're making, very deterministic thing that we're doing for assignment 3 and 4. We're not asking you for any kind of, variability at all, because that would be too difficult to code. We just want you to do some basic things for assignment 3 and 4, and that's why, it's deterministic. But if you think about it, right, in a real world scenario, if we're having a video game and you've gone through, that type of enemy, and you know exactly what they're going to do every single time, then you know how to defeat them already, as an example. And that can become, it can break the immersion again, your engagement in the game. And when you're not engaged in the game, you're like, well, okay, so I know how to defeat them. Sometimes people like that. They like to be able to defeat AIs. Other people will find it so that it's not so challenging, and then they get bored and they play something else, right? After time, especially if it's repetitive, okay? So here's our, let's go back to our room entering enemy as an example. Let's suppose they decided to smoke the player out as an option, right? They might need to get matches and gasoline. So here's the other option. This is the scenario here. But it wouldn't matter in which order, as long as both matches and gasoline were in place before they tried to start the fire. So I don't care which one it is in that sequence. I want to get matches. Can I get matches? Yes. Cool. Can I get gasoline? Good. If I can get both those two things, good. I have matches and gasoline, I can smoke them out. But if I don't have those two things, then I can't smoke them out, so the entire sequence fails, right? So that's how it works. So again, it's kind of interesting, depending on which one they want to go for, matches or gasoline, they're going to go for the one, maybe the one that's closer, or some random sequence, okay? It doesn't really matter. So again, we can call these partial order constraints as opposed to strict order constraints, because strict order means you have to follow the order that you programmed. Partial order, or creating a random selector, it's kind of similar to a regular selector, but what it does is says, okay, while true, so while I'm true, then I'm going to choose a child, one of the child in the children array, as an example, take that children array and select a random child. If I can run the child, then return true, right? And it's going to keep running, as an example, until something is returning true, otherwise return false. So again, it gives us some randomization, but in this particular case, the way this has been written, it's not going to give up even if all of the children are failing. So it'll keep trying different things, as an example, in different order, until some task is, kind of completed. So that's one way of creating this partial order or randomized, composite task. A better approach, though, is we walk through all of the children in some random order. And what we can do is we can do this for either selectors or sequences, using some kind of suitable random shuffling function. And it can be implemented like this. So again, you have a children array, and here's for the non-deterministic selector again. And what you do is you shuffle the children, so create a new array. And for every child in the shuffled array, then you want to run, for the first one that's run true, then you return true, otherwise you return false. Okay, so that's how the non-deterministic selector works, and it's similar for the non-deterministic sequence. As long as none of the random children that are put in the shuffled array run false, then the entire thing runs true, and that's what you it's kind of sticking to the the type that we're talking about here. Okay, and I'm not going to talk about how to shuffle tasks. And so the non-deterministic task, again, it does one or the other, right? So that's what this little kind of tilde means. Okay, either barge the door or try and smoke them out, as an example. Okay, and one of the things that you can see here as well is it's a sequence, and this sequence is a random sequence. This is a random selector. So it doesn't matter which one you get, whether you get matches or gasoline, as long as you can get both of them, then this whole thing returns true. And then therefore you can do this, kind of strict order. I can douse the door and then I can ignite the door and that'll smoke them out, as an example. Okay. And if randomly the AI decided to do this part, this subtree over here, then, one of these three selectors would work. And again, it's going to try, the regular selector is going to try them in order, and this is going to be a partial order. Okay, so far we've talked about, a few different types of tasks. We've talked about a selector type task. We've talked about a sequence type task, and we've talked about just a regular task. There's other types as well. Remember, we talked about conditions, actions, and composites, right? Conditions, actions, and composites. And there's a fourth, which is really significant, and they're called decorators. And what decorators do is they modify, as an example, it wraps the class that it's supposed to affect, and it modifies the effect of that class. A couple of interesting ways of doing this is if I want to repeat until fail, that could be a decorator, okay? Let me talk about those in a second. So, so it modifies the behavior, of, as an example, the task that it's decorating. A lot of times when we think about decorators, we also think about them as filters or modifiers. Okay, that's what they look at. Okay, so that's what how it would kind of work. So here's an example, of a decorator type. Okay, so if I had a decorator, if I wanted to make a class called limit, right? So that's, remember, limit is a decorator. A decorator modifies a regular task, right? Because a decorator is a type of task. Then I can set up a run limit. So here's an example of where we only want to run the task a number of times. Okay, so if the run limit is an integer and how many times the task has been run so far, if run so far is greater than or equal to the run limit, then return false. We can't run that task anymore because, we've run it as many times as we're supposed to. We've tried a couple of times, right? So example, you might have an enemy that tries to barge the door a couple of times. They break the door once, they don't break through. Okay, let's try it again. They try again, they don't break through. Maybe they try a third time, 3 strikes you're out, and the task has failed if the door is too tough, as an example, okay? And this could and you might say, well, wait, how do they barge the door? Maybe you do random damage every time you hit the door, and the door has a certain number of hit points. So let's suppose I have a door that has 30 hit points, right? And every time I hit the door, I can do, I don't know, something like 2d6 damage. So up to 12 damage every single time. The average is going to be 7 damage, right? And chances are the enemy's not going to barge through the door, because if they do an average of 7 damage every attempt, and there's only 3 attempts, that means I can only do 21 damage on average. And if the door has 30 hit points, as an example, then I won't be able to go through. If the door had 20 hit points, chances are I'm going to make it through the door, because on average, I'm going to get 7 damage every time. Okay, but what if I didn't? What if it's RNG? What if I got it so I tried a few times and I couldn't get through? I'll stop trying. That's what this thing does. It limits the number of attempts that an AI will try the task, and that's what the decorator would do. Decorators modify the task that it's trying to attempt to do. Okay, so it's kind of interesting. So until fail, that's another type of decorator. Until fail is like, it's going to keep trying that task until I can't for some reason. Okay. So again, I'm going to keep running this task until the entire thing fails, as an example. And the entire thing might fail. The until fail thing means that maybe it's very difficult to fail. Like I have a selector, and I have a number of different kinds of children that I can attempt, and I'm going to try all the different combinations of children. Maybe it's random even, and I'm going to keep trying it until I've tried all the children. And I know that if I've tried all the children and they've all failed, then the entire selector has failed, and that's where I'm going to keep trying until I fail. Here's an example of kind of behavior tree that we can use the decorators with. Okay, so we can start off again with a selector sequence, right? Selector, either one or the other. Let's start with this one. This is a strict sequence. Remember, there's no randomization. So, okay, is the enemy visible? Yes, let's say, right? If the enemy is visible, until fail, what am I going to do? This decorator modifies this sequence. So what until fail means, I'm going to repeat this sequence over and over again. Let's think about this. So here's the first part of the sequence. Am I conscious? Yes. Hit the player. Okay, next, pause, hit him again. Okay, until fail. Did I fail? Am I still conscious? Now this could be until the player is conscious, if the player is not conscious anymore, right? If the player is conscious, yes, keep hitting him until he's unconscious. That could be the other way to think about this. And then when he's unconscious, this fails. And if this fails, as an example, then it kind of comes to this point, right? So this is until fail. And until fail means this is true. It failed. So true, visible. Okay, now restrain them if they're unconscious, right? So this whole side is true. But if the enemy is not visible, the player is not visible, let's say for the AI, then this whole sequence fails, right? And then we try we go to the right child of the selector. Okay, let's try the right child. Okay, cool. So if we go to the right child, we go, okay, so we're going to try this one first in sequence. Can I hear them? Well, then creep around, right? Good. If I can't hear them, this thing fails, and I try and just move around. Okay, this is what this does, a patrol. So again, you can see how the until fail, what it does, it keeps making me do that same action over and over again without having me to go to the top of the tree again. Okay, so kind of, again, very straightforward, in the way that it works. And for the most part, it's just another modifier. It's a modifier that adds more complexity, to the behavior. So filters, we can modify the status code returned by a task. So if the status code might be something like, trying to true or false, an inverter node is very interesting. And an inverter node, what it does, it says, okay, whatever, if it returns true, then return false. Okay, as an example, if this returns false, return true. We want it to fail. We're waiting until this thing fails. Okay, now go to the next thing. Okay, so this is kind of interesting too, where you don't have to let a sequence stop the entire process. You're expecting the sequence is going to fail at some point, right? And you've tried. You want to show that you want to have the AI do a certain number of things, as an example. Okay, so this is kind of interesting where you can use an inverter. And here's what a decorator would look like. A decorator is just a task that has child tasks, as an example, a child task that's relating to it. So a decorator only has one task. That's the difference, right, between a decorator and a regular task type. And that child task is the thing that it's modifying. Okay. So we can guard resources with decorators. And again, the way it works is it's a test to say, if the resource is available, then go ahead, do it. If it's not available, don't even attempt this task, because otherwise what's going to end up happening is, you're going to have issues, doing something. For example, the animation engine, is it available? Yes. Okay, then play the animation. Okay. And this is a way of guarding resources, right? Okay, I'm just going to move on from the semaphore thing, and I'm going to talk about a couple things more in terms of concurrency and timing. So what happens then, so far we've managed to avoid running multiple behaviors at the same time. So here's an example. Decision trees, they're intended to run quickly, and they give a result that can be acted upon right away. Okay, so they kind of bubble down to some kind of result, You have a bunch of conditions or actions, and the result is going to be, it's going to result in an action that the enemy is going to take. State machines, they're long-running processes, but their state is explicit. So you can only have one state at one time. That's one thing that is interesting. So it's easy to run them for a short time each frame, and kind of processing any transitions that are needed. Behavior trees, though, are different, and behavior trees are different because some actions, there might be some actions that have no time to complete, and some actions that take time to complete. So what do you do? Like if that action takes time to complete? For example, moving to a door, playing a door opening animation, and barging through the door all take time to do, right? Because there's got to be a sequence. It takes time. So you have to wait for for one thing to finish before you go on to the next thing, or before you report success or failure. Okay, so that's something to think about. So again, so far the behavior trees we talked about, the actions that we're trying to accomplish, they complete instantly, right? And unlike most actions, we want to schedule some stuff in a game. So to improve the situation, we need to assume some sort of concurrency. And I want you to think about concurrency as a multi-threading, okay? So the ability for multiple bits of code to be run at the same time. But it's really not the same time, right? Whenever we do, and again, this is how I always think about multitasking back in the day when multitasking first, we had multitasking processors. It's not really multitasking. It's just basically going to go from one task to the other task, the third task, and go back, right? And sometimes it does it in a random order, kind of decided by the server. But all tasks get an amount of task time that they're going to run. And what happens is, it seems to us as the user, because the processors might have multiple cores, that they're all running simultaneously. But really what's happening is they have a task time, and it's like they're running simultaneously, but they're running in their own thread. And the problem with this is, if the threads aren't, if the tasks that we're running aren't thread safe, that means sometimes we'll try and to run the same task twice or something like that. And that could lead to a problem. So I'm just telling you, this is sometimes what's required, where I want to have this task, kind of complete. I'm waiting for this one task to go. Meanwhile, I can be interrupted by doing this other task, because I'm also doing something else at the same time. A good example of that is keeping alert, right? So I'm keeping alert. I'm in the middle of playing an animation, but something happens. Remember we talked about some kind of alarm condition. That alarm condition interrupts what I'm doing, and an interrupt is something that's going to stop the sequence or stop the selector, and it's going to fail. It's going to make it so that it fails that selector, stops the action that they're taking, and do something else. Okay. All right. So that's a little bit about concurrency and timing. And so sometimes what we want to do is create this pause task or a wait task, right? And so wait is a type of task. And what it does is it has a duration that you want to wait for. And what you're doing is you're going to sleep for some time. And the reason why you want to sleep is a bunch of different things. Sometimes we want to sleep because we want to keep doing that action for a while. Otherwise, what we're going to do is we're going to see that actions become jittery, like we talked about. So imagine every frame you're making a decision, right? And let's suppose you're making a decision like you are healing yourself, and healing takes time. Maybe you have to drink a potion or you have to brew something. And that, I'm talking about if you're an AI, let's say the mind of the AI, right? So it's kind of brewing a potion, and it's kind of going through the sequence of making a potion for itself so it can drink the potion so it can heal itself. So it takes time to do this kind of thing, right? Then what you want to do is you want to wait. Sometimes the AI is going to wait until the potion is finished brewing. That's a sleep task. They're just sitting there idle, as an example. And then when the potion is done brewing, right, or some length of time, we can assume that time is the time it takes for the potion to stop brewing. Let's suppose the AI stops sleeping and then goes on to the next task, which is drink the potion, right? And when they drink the potion, the effect is going to be immediate. They're going to get health back, and that they've completed that part of the sequence, which is heal yourself if you're low in health, as an example. Okay, so that's kind of what we can do. We can have this wait task that helps us, perform things, especially things like that take time more efficiently. Sometimes also what we want to do is we also want to talk about things that run in parallel. So again, we can make use of this third composite task, which is a parallel task. And along with the selector and sequence, it kind of forms the backbone of almost all behavior trees. So by the way, parallel tasks and multi-threading is a good reason why behavior trees are so popular. They're so popular because I can run tasks at the same time as another task, and I don't have to wait. I can assign different tasks to different cores, and then I can have that happen for the AI, almost like they're doing two things at once. Okay, so kind of an interesting way of doing things. And that's why you'll see a lot of them. If you actually look up behavior trees, you'll see parallel tasks, and usually they're kind of the image for that is like 3 lines, almost like a little a line, 3 lines on top of each other is usually a parallel task, is what it's called, right? So so it acts very similar to a sequence task. It has a set of child tasks, and it runs them until one of them fails. Okay, that's what it does. If all of the child tasks complete successfully, then the parallel task returns with success. And in this way, it is identical to the sequence task, and it is also non-deterministic, right? So the difference is the way that it runs those tasks. Rather than running them one at a time, it runs them all simultaneously. And we can think of this as creating a bunch of new threads, one per child, and sending the child tasks off together. Okay, so think about a scenario that might be good with that one. Okay, so again, so then we can modify our task class with an additional method, right? Which is we have 2 methods. We have a method that runs either true or false, and we also have a method that terminates, right? So again, no return type, but the terminate method stops the task. We can interrupt a task in the middle if we need to, okay? So again, when one of the child tasks ends in failure, the parallel composite task will terminate all of the other child threads because unilaterally, because at the end of the day, they all have to succeed, right? But we're not going to wait for all of them to be attempted or to continue until fail. We're just going to terminate it as soon as we know that one fails. So it's like a sequence task. As an example, parallel is a sequence task, but it's a sequence task that runs everything all at once, okay, as an example. So here's the example. So a parallel task has an array of children, tasks, a task array, right? And it holds all the children currently running. So here's running children. So we have a new, again, a new array for all the children that are currently running, because not all the children are going to run. Maybe they all have different time frames in terms of how long they're going to take to complete. And then what happens is we have a function that returns true, right? As an example, the result starts off as null, so we run false first, and then what we do is we run each child, right? And we add to the running children the child that we're running. We're going to try and run that child, and we keep doing that for each child in the sequence. So we run all the children. We have keep track of all of them, all the children that are running, but each child has its own thread, if you will. Okay. And then if any child terminates, then terminate everything in all children in the running children array. That's what it kind of does. Okay. So again, if you look at this diagram, let me zoom in again. We can see that we have a non-deterministic sequence, right? So one of these 3 is going to run. So randomly, we choose this one. This is a parallel sequence. So non-deterministic selector, parallel sequence. Parallel sequence means it's going to run each of these things simultaneously, okay? So here's a scenario where you could run 3 tasks simultaneously. So now this, instead of it being a scenario where I'm running 1 brain, I'm running 3 brains at the same time. So here's soldier 1, soldier 2, and soldier 3, okay? So you can see that soldier 1, soldier 2, and soldier 3 are all going to run simultaneously. So let's check soldier 1. Soldier 1, does they have ammo? Yes. Well, then attack. Soldier 2, do they have ammo? Yes. Then is soldier 2 in cover? Yes. Then do a sniper attack. Soldier 3, do they have ammo? Is there an exit route? Yes. Then they guard the exit route. So if the only way that this whole parallel task is going to run is if each one of these things, which is activated simultaneously, all these things are running simultaneously, then this whole sequence passes. Otherwise, this sequence, this child fails, and we try one of the other two things, either take cover or retreat for the entire crew, okay, as an example. So it's kind of interesting. You can use this for tactics for the entire, for more than one AI as a good example of how this can be used. Okay. And parallel tasks are also good for condition checking. Okay, so again, here's a sequence, and imagine if there's, there's a sequence that has to run in strict order. So is the player in position? Yes. Then use the computers, right? But here's a parallel, kind of a parallel task, a parallel sequence. So, and it also has a decorator. Remember, decorators are kind of like this. And what decorators do is they modify the single task that belongs to them, right? So until fail, until not in position anymore, right? Until fail, get into position, basically is what this is going to do, right? And then if I failed, at the end of the day, right? So basically the player is going to stay in the same position as an example, the entire time. Why? Because both of these two tasks run at the same time. So I run this task group, and this task group at the same time. So I use the computer and I'm in position. I keep staying in position the entire time. Maybe that means keep moving into position while I'm using the computers. If one of these two things fail, this entire task fails. So if I can't use the computer or somehow, I fail to be in position, as an example, then this entire thing fails. Okay, so it's very interesting in terms of guarding resources, but also it's interesting in terms of when you want to do two things at the same time. Okay, so here's the behavior tree version of a state machine. All right, so again, take a look at this. So here's a selector sequence. Either one of these two needs to be true in order for the entire thing to be true. We're going to start on this side because it's a regular selector, right? And then from here, it's going to run these two tasks at the same time. Remember that little robot that keeps everything tidy around the station? This is what this thing is, right? So like we talked about last week. So, okay, so until fail, is there trash visible? No, it failed. Cool. So if this failed, then this whole thing fails, then we come up here, okay? So why? If there's trash visible, right, then I'm going to keep moving, and then I'm going to keep tidying the trash because these two things are going to run at the same time. Okay, cool. What if this whole thing failed? So I don't see trash. This whole thing fails. I come up here, and now I have another parallel task that I'll run until fail and recharge. So take a look at this. And it says until fail has another filter or another decorator, and the decorator is an inverter. So the inverter says, is the trash visible? If the trash is visible, true, then it returns false, right? And if it returns false, then it failed, right? If the trash is visible. Then if it failed, we stop this entire sequence. We stop recharging, okay? That's how this works. However, what if the trash is not visible? No, it inverts it, true. So until fail, it keeps on going through and make sure that there's no trash visible. And if there's no trash visible, let's say in the entire station, it keeps recharging because these tasks are running parallel. Okay, so another interesting way of representing the same thing. A little bit more complex, especially when these parallel tasks are introduced. But for the most part, it's not so terrible. Okay, that's concurrency and timing. So again, intra-task behavior, and the tree shown would never return as long as the player didn't move out of position. Like we said before, the character would perform its actions and then stand around waiting for the until fail decorator to finish, which of course it won't do as long as the player stays put. If the player moves, going back to the previous example here, right? If the player moves, then then that whole thing would fail. Okay. Okay, so we have another one, which is an interrupter. An interrupter, again, extends a decorator, and the interrupter can interrupt an action, similar to us waiting for an action to happen. Again, I'm not going to go through the pseudocode here for you, but the idea here is that you can have different kinds of decorators that make it more complex or create more complex behaviors potentially. Okay, I'm just going to skip through. So here's an example, right? Using parallel and interrupters to keep track of conditions. All right, so this is something that you can keep track of, right? So example, now this is a parallel task. You have an interrupter, and then that's a decorator, and the interrupter basically will interrupt all the other tasks that are playing at the same time. Because remember, this parallel task runs these three tasks at the same time. It runs them on different cores using concurrency or using multiple threads. Okay, so again, it does the interrupter, it uses the computers, and performs the interruption all at the same time, right? As an example, and that's what is running. Can I perform the interruption? As an example, it performs the interruption if I'm finished using the computer. As an example, remember, each of these three things can take different lengths of time to complete. Okay, we can also so far we've talked about adding conditions, actions, and some kind of composite tasks. And the composite tasks make the decision tree what it is really at the end of the day. So so we might have a subtree in this case that represents smoking the player out of a room. Going back to that idea, right? If this was a subroutine or a function, it would take an argument to control which room to smoke out. So example, it would be something like this. I indicate which room to smoke out, and then I fetch my matches, I get my gas, and then I douse the door and I ignite it. Okay, so those are all the different actions that I would do if it was a function, right? But if we look at it in terms of a sequence, here's a sequence. Is the enemy visible? True. Cool. Select an enemy and write this to what we call a blackboard. And the blackboard is almost like, I want to write it to memory. I want to have almost like a set of states that I turn on and off. So yes, the enemy is visible, and I want to select the enemy that I want to, that I'm talking about, because there could be multiple enemies in this case. Maybe there's two players or whatever. Or maybe the AI can attack both players and other AIs. Okay, they can determine any one of them as an enemy, right? So select an enemy. Okay, cool. True. This is going to always be successful because at the end of the day, I should be able to select an enemy unless somehow the enemy I'm trying to select is not visible anymore. Okay, going back to the selector node, this sequence node, I'm going to go back to this selector, and now it says, okay, either one of these can work. So here I'm going to have a sequence node. Is high ground available? No. So this whole thing fails. And notice there's a thing here that says always succeed. Always succeed, which means, guess what? I'm going to return success here because I'm checking to see if there's high ground. This is a way of doing that, right? And I can do that without interrupting my sequence. So always having a thing that always succeeds is interesting. It's a way of kind of always returning true, okay? So that's a different type of task. And then, again, here's an example of, okay, fine, engage the enemy and figure out which enemy you decided to engage that we selected, whatever that selected enemy is. And we say blackboard. Blackboard, like I said, is some kind of global variable or something else that we're going to have just in the enemy's brain to kind of say, this is the enemy we selected. Here's the current enemy, whatever that current enemy is. All right, so I've talked about behavior trees, and hopefully you got it. So here is a possible diagram for assignment 4 again. So think about assignment 4, and we talked about last time using state machines. Here's an example of if we're going to apply for assignment 4 for the close combat enemy. It looks like here, a behavior tree. So let's think about this. So here is a selector sequence. Either one of these two can be true for the entire selector to work. This one is repeat until fail. Okay, so here's repeat until fail. This is a sequence node. So sequence node is going to go to the first sequence, and the sequence node is going to say, so here is a selector. Either one of these two has to be true in order for this to work. So let's do the annotation again. So is the player detected? No. Fine. Then try and patrol. I'm in patrol mode right now. Okay, I'm returning patrol node. That's my state. That's my action. I'm returning it back up to the sequence, and it's checked. It goes here. And now I go to the first one. Is the player in radius? So player's not detected. I'm patrolling right now. And is the player in within radius? No. Okay, so then move to line of sight. Move to line of sight. Check mark. I'm moving to line of sight. This still is in sequence. And now return until fail. I'm going to do this in sequence. This next one in sequence. Do I have line of sight? Yes, because I moved to line of sight. So far I'm returning true, right? And then good. Now, am I within close combat distance? No. Well, then move to the player. That returns true and move to the player. Now that I'm in the player, attack. I attack the player. Good. And now here, these are inverter nodes. So inverter node means that whatever this is, if the player is not dead, is the player dead? No. Well, this returns true, so we keep going. And is my health less than 25%? No. Well, then keep going. So then it didn't fail, so I go back to line of sight. Do I still have line of sight? No. Okay, I go back here. I've lost line of sight. It failed. I go back here, and then I come back to the top here. And because this whole thing failed, right, then I stop. So this is an example of something that might work. And you can see how this might describe something that is that makes sense for assignment 4 for a close combat enemy. If you're going to use behavior trees instead of using decision trees or state machines. Okay, makes sense? So that's how these sequences work, sequences and selectors. It's interesting. You can also think about other possibilities here if you want to run things in parallel. You want to run all these three things in parallel at the same time, then this would be a parallel node instead of a regular sequence node. What if we made this a parallel node instead, right? So a parallel node, if we did that, and this is the exercise here. So let's suppose instead of this, we made it a parallel node. So we'll call it parallel, right? So if we did a parallel node, let's just make this so that it's something that you can see. So parallel, or we'll make it an equal sign. Okay, so just because it's like a triple equal sign, right? That's what a parallel node looks like in many ways, right? So let's bring that back up to 24. So if it's a parallel node, then it runs these three things at the same time. Okay, so again, running in parallel for us, for our little SDL engine, where there is no concurrency that we've kind of enabled. So it's hard to make this node work by running all these three things at the same time. What we could do is we could simulate this by having different tasks that are going to be checked at the same time, and each one of them is going to be set in order in the update method. All right, but if we could do it, if our engine had the capability, think about this. So these three things are running in parallel. So let's see. So I'm going to try and is the player detected? Am I in radius somehow? Okay. Is there, can I run this thing all at the same time? Which is do I have line of sight? And then if any of these three things fail, then this entire thing fails and it's going to keep going until failure, right? So yes, it could work, but I think it works way better just as a regular, a regular sequence node. The other thing to note is if the player is detected, here's something else we could do that we didn't put in here. We could also say, write this to the blackboard, right? So write to blackboard. So remember, blackboard is just our fancy way of saying write it to memory or hold it inside of, kind of keep note of this, that if the player is detected. So if the player is ever detected, right, then this is always going to return true, this piece, okay? This is always going to return true. And the reason why we want that is if the player is detected, then we're never going to patrol again. We're only going to ever patrol if the player is not detected, okay? Does that make sense? So once the player is detected in our game, they've always been detected forever and ever. And that makes sense for us because, you know, if we go through the sequence one time, this whole thing, it's going to be like, well, we've already had line of sight before, which means the enemy knows that the player exists, right? So that's something that we could think about as well. Okay, so remember that if we run this in sequence and I go down here for the first time, and if I'm coming down here, and this is kind of keep going until failure or repeat until fail, that's what this node is, and it's a decorator node. Remember, decorators only have one task that they have inside of them. Let's go back to this again. So here's the sequence. Go back to here. Is the player detected for the first time? No, then patrol. Okay, so we write to the blackboard that the player has not been detected, right? And if I'm within radius, we write this to the blackboard, right, that the player has been detected. This is another one we write to blackboard. So, and the reason for this is because, like we said before, once the player is detected, they're always detected. Okay, so I'm just going to move these around so we can see these in a little bit more detail here. Okay, so is the player within radius? Then good, write that we're detected to the blackboard. You know, as an example. If not, then move to line of sight. That's the move to line of sight action. Cool. So this returns true, and it goes back to here, and then until fail. Okay, do I have line of sight? If I have line of sight, guess what? I write that the player's been detected to the blackboard for the first time. So I'm never going to go back to patrol again. I can't go back to patrol because I know that the player exists, right? If I know that the player exists, then I'm not going to be, I'm going to try not to be a dumb enemy, as an example, because, you know, this way the player's always going to try and go back to patrol mode, which doesn't make any sense, okay? I'm just going to try and move these around for you so you can see what the new state would be. And of course, I'm going to miss something because, yeah, that's what happens. Okay. That to that. There we go. There we go. So it kind of almost worked, but anyways. And I think this one has to move to there, and this one has to move to there. All right, so that's kind of how it would look. So let's, I mean, again, if you consider what this would do, here. So now that I've got line of sight or radius, or if somehow I'm already been detected, right, from the beginning, that's the first thing we check. We check to see if the player's been detected, almost like a Boolean. Detected, not detected, true, false, right, as an example. We set that up. And then in the sequence, this then, as soon as we're, you know, we've written to the blackboard that they've been detected one time. If we ever have line of sight one time, then, you know, as an example, then we're always going to have the player detected. But let's go through this again. So I move to line of sight. That means in order for me to get here, I've been successful, right? I've been successful. If I can't move to line of sight for some reason or not, right? Then if I can't move to line of sight for whatever reason, then this node will fail, and so this whole thing will fail. This whole thing will fail, and then I won't even come to try and do you know, to check if I'm in line of sight or not, right? But if we assume that we can never not move into line of sight, that it's going to keep moving until it gets to line of sight. It's going to keep doing this. We could also have another decorator node that says, you know, keep moving till we have line of sight. Keep moving until we have line of sight, right? That could be another subsequence with one of these things to say, you know, until fail, move to line of sight. Okay, now check to see if there's line of sight. Good, we have it. Good. And then now that we have that and we have line of sight, well, are we within close combat distance? No, then move to the player and keep moving to the player. We can also have in here another move until fail, right? You know, keep moving to the player until there's no more, we can't move. And we can use an inverter to make all this look, kind of work in a nice way. Okay. So that's kind of just a possible set of scenarios. Now it looks complex, but the thing is it defines, a set of sequences, and we don't need to use both a super hierarchy, like for example, a hierarchical state machine and a decision tree at the same time, like alarm conditions, right? Or an interrupter of some kind. Okay. Questions around behavior trees. So you've seen the three major types. You've seen decision trees, you've seen state machines, and you've seen behavior trees. Which ones do you like? Anyone offer an opinion about what they would use if they were coding? What are your thoughts? Maybe you've used something in the past and you have a preference. What are your thoughts, guys? Hopefully you have some thoughts. Maybe you just don't like any of them, or you don't know, but it's still a thought. So again, to me, what speaks to me the most is something that looks like this, or a combination of decision tree and a state machine, which decision tree and state machine combination makes sense because, again, talking about that alarm condition, this idea of where health is less than 25%. Here's the other alarm condition: the player's dead. If the player's dead, then why am I going to keep going, right? My enemy, whatever the enemy is. It could be the player or it could be other enemies. Maybe I'm going to make an AI that fights other AIs, right? And until, I have less than 25% health, or until my enemy, any visible enemy is dead, right, as an example, then I'm going to keep going. I'm going to keep going, or I'm going to flee, one of the two. Okay? So again, the only way this bottom sequence can fail is based on, something like this, where I don't have line of sight somehow, right? Or I'm not able to move to the player, or I can't attack somehow because the player's moved out of range, or the player is dead, or, my health is less than 25%, right? So one of those three things, or one of those things is going to make me fail. And if I fail, it says keep going until fail, which means keep checking to see if I'm line of sight. Keep checking. You don't understand behavior tree yet. So again, behavior tree, the way it works, Derek, is you have a sequence or a selector. So this is a selector, either one of the children. As long as any one of the children are successful, then the selector node is successful, right? For a sequence, that's a sequence node, all of these things are going to be run in order, right? And all of them must return true in order for my sequence to return true. Okay, that's how that works. And then we have decorators. Decorators modify the single task that is underneath them, right? So here it's kind of keep looping until fail, right? Repeat until fail. That's the idea, right? So that's a decorator. And here's another type of decorator. Usually they're in diamond shapes, and they're just an example of, basically this is an inverter, and the inverter inverts the results. So if the player's dead, if the player's not dead, then that would be false. And if it's false, this would fail, but the inverter makes it true. False turns to true. And then, so the player's not dead, that's true, good. Okay. My health is not less than 25%, that's true, good, keep going. Keep check to see if I'm in line of sight, good. If I'm in line of sight, then keep on attacking. Or if I need to be in close combat distance, move to the player again. Keep moving to the player. The only weird thing is if somehow I lose line of sight, then this whole thing fails. And if this whole thing fails, then it'll end up that this whole thing fails, and then I'll leave somehow if I lose line of sight. And that doesn't make sense. So there's something missing for the diagram that I drew. Okay, so that is A4. I also wanted to talk about this week's lab. Some of you did not attend, and it's always I'm always worried that when you don't attend, you don't understand. And I also want to talk a little bit of administration with you guys. There are people in our class who have not yet completed a lab. Remember that our labs are worth a great pile of marks. at the end of the day, right? And you can always find that out. You can always find out how everything is set up here in my course information. Under the course outline, if you're not clear on something, you can always look at the course outline and see where the evaluation comes from. So notice that labs, we take the best 11 out of 13 of the labs, and they're worth 44% of your final grade. So if you never do a lab, but you do all your assignments perfectly, the maximum you can ever attempt or you can achieve in this course is 66% or 56% actually, right? 56%, right? So that's pretty tough for you not to do a lab. So people who haven't done labs, as an example, get onto it, because again, I'm taking the best 11 out of 13. That means you can miss 2 lab parts. Okay, you can miss 2 lab parts. You can actually miss 8%. 8% will be forgiven. So if you miss 2 lab parts, let's say, for example, you do a lab, but it's worth 2 labs, so lab, it's worth 8%, and you missed the entire thing. For example, lab 6 was worth 8%, right? You missed the entire lab 6. That's okay. If you do all the other labs, you still have a chance to get 44%. Okay, that's how it works. But if you miss lab 6 and you miss lab 7, which is worth 12%, that's 3 lab parts, right? Or let's say you do lab 7, but you only do part 1 and you don't do part 2 and part 3. And so when you do your lab report, you're missing 2 parts. That's okay, because those 2 parts are 8%. So you're still going to get up to 44% if you did everything else. But please don't miss every one of your labs, guys. This is death for you guys when it comes to a GPA. That's where most of it comes from. There is no final test in this course. There is no midterm test in this course. It's all labs. It's all practical work that you have to do to understand how this is working. Okay. And this is where the marks come from. So please, always look at this as a guide to where your evaluation marks are coming from and how you're going to do in the course. This is a very clear guide on how you're doing, right? So again, if you're someone who's never done labs up until this point, and we're sitting at week 11, right? Take a look. Here's all the labs, lab 1A, 1, 2A, and 2B. That's, if you miss lab 2 altogether, that's okay. But if you miss lab 2 and lab 3, right, then you're down 4%. Maximum you can get is 40, right? If you miss lab, 2, lab 3, and lab 4, well, now you chop off another 8%. So the maximum you can get is 32 out of 44 for that one. Okay. So please make sure, you get them done. And if you're someone who's had challenges, or if you missed something, let's say last week you couldn't get your lab 6 submitted for some reason. Remember, there was 2 parts, and I also give you a chance to restart lab 6.1 with a starter, lab 6.2 starter that I gave you. So for example, if I know some people found the video wasn't working properly, it's okay, because lab 6.2 started with the starter. I gave you a starter to start with, to restart, right? From lab 6.2, and you can still finish lab 6 as an example, because lab 6 needed 2 parts. There was a part that was for you to do on your own, and there was a part that I gave you together by the end of the 2nd week. Okay, so please make sure if you haven't done that, communicate with me, because again, there's some people that they need help with labs. You need to finish your labs, guys. So what's left, if you think about it, and again, this is inside of our structure as well. If I go back up, and I'm just talking administration here because I'm concerned, right, for some people who haven't done it. Lab 6 was a 2-parter. Lab 7 is a 3-parter. That's 12%. It finishes week 13. All right, and then notice that there is a lab for week 14, and there is no lab for week 15. Week 15, there's no lab. There is just assignment 5 presentations for the last week of class, okay, which is what you're doing. You're presenting your assignment 3, 4, and 5. And your presentation, it takes the place of an assignment. So there is no lab for machine learning for the very last, kind of lecture that we're going to have, okay? Just to keep in mind. So during our lab times in the last week of class, you're going to be doing presentations for that whole time frame, okay, for you and your assignment 3, 4, and 5. If you do not present, or if you do not finish your presentation, your assignment 5, you lose 6% of your final grade. All right, so that kind of is like, you know, an assignment or a lab, but it's part of A3, 4, and 5, and it's supposed to be done with you and your partners. Which means that really there's only lab 7 and lab 8 left. You know, so those are the only 2 that you have to do, because we're in the process of doing lab 7.1. We just did it. We just finished it. So next week when we get together, when we continue lab 7, it's going to be lab 7.2, and this will be lab 7.3. So if you do all those 3 parts, there's 12% of your final grade if you get it done properly. So please, guys, if you haven't had a chance to do it, then there's a chance still that you can still get, you know, just for in the second half that we've worked together, there's 4%, 8%, right? And an additional 12%, that's 20. And then lab 8 is another 4, so that's 24% of your final grade is the labs we're doing in the second half of semester. Okay, I'm mentioning this to you because there are people out there and who are going to watch this recording. They're like, yeah, I'm in trouble. I haven't done a single lab. Okay, and if you're one of those people, there's still a chance you can do okay. All right. All right. Questions around labs or assignments or anything else? How about any issues? Let's talk about assignment 3, 4, and 5. Do any of you have issues with assignment 3, 4, and 5? Again, this is your chance to connect with me and talk with me about it. If you want to talk after class, I can certainly stop recording right now, and I'll talk to you one-on-one after class, and we'll just end the class right now, if you prefer that. Does anyone need to talk with me, is what I'm asking. Anyone here physically need to talk with me? No, one link is fine, Vander. Vander was asking, should they have submitted two GitHub links for lab 6? One is good, because lab 6 is lab 6. It's not 6.1 and 6.2. For you, it's one big lab. Same thing with lab 7. Okay, so lab 7, you're only submitting one GitHub link, right? I'm giving it to you in parts, right? Part 1, part 2, part 3. We're building it up over 3 weeks, right? That's why it's worth 12% of your final grade. But you know, it's just one GitHub link. Yep, absolutely, Karen. You can do that. Okay, so that is it for me. If there's no one else, then that's it for today's class. Next week, remember what we're doing next week. So week 12, we're going to be talking about something called goal-oriented behavior. So far, and rule-based systems. So far, our AIs don't have any goals. They just react. They just have some behavior based on their internal or external knowledge. That's what they're going to be. That's what they do now, right? But in the future, we're going to maybe give them up, you know, kind of front load them with some goals. Maybe their goal is to protect the base. Maybe their goal is to collect resources. Maybe their goal is to, you know, seek out and kill all players, you know, whatever. But they could have some kind of goal that they're going to follow, almost like a moral code. Or a list of things that they're priorities that they're gonna go with. We'll talk about goal-oriented behavior, and it leads us into in the second set of topics. The first set of topics we've completed, which are making simple decisions. That's what these 3 things are, or maybe up to more complex decisions. But the second set of topics in the second half of semester are all around priority. You know, what is the most important one of the decisions to make, and why would I choose to make that decision if I was an AI or not? Yeah, if you stick around after class, Marco, we can talk about it. Okay. All right. So that is it for today, and I'll stop recording this, and then I'll stick around for anyone else who has to talk to me. And then if you want to message me on Discord, you can do that too. Thanks, and see you on Tuesday. Oh, one more thing before we go. Remember, next Tuesday, we're physically in class together. We're actually in person for week 12, because that is what Philip is going to do with you with game production. Game production is going to be in person. You and I are going to be in person too. So please plan to be in class on Tuesday of next week. Okay, because we're going to be in person next week. Okay, thanks very much. And I'll stop recording this. Thank you.